Okay, so Farhan has asked a question that how does, what is Lie algebra, how the Levi-Civita symbol, comes into play and things like that, right, Farhan?
Yes, sir.
The place, we have seen examples. So for example, we have SU2 matrix. I'm just trying to make contact with what we have seen. And we saw that, these matrices, because they're continuously connected to the identity, we can write them as some exponential of something. So exponential I, this is the physicist's choice. And because SU3 is three-dimensional, there are three independent real parameters. We have a set of three real numbers parameterizing an element of SU3. So we can kind of write that U is a function of, say, three real parameters alpha, and then that dotted with three generators T or tau.
So does this mean alpha 1, alpha 2, alpha 3? So alpha, if has three coordinates, it will give rise to three unitary matrices.
Yes, in general. So for example, if alpha is a set of three numbers, right? Alpha 1, alpha 2, and alpha 3. So it may be that, possible that alpha 2, alpha 3 is 0. In that case, we have just, our matrix depending on alpha 1. In that case, this equation becomes I alpha 1 tau 1. Okay. Similarly, we can have U alpha 2, EI alpha 2 tau 2, U alpha 3 is EI alpha 3 tau 3. But it can also be that it can be any general linear combination of these these t's, right? So it can be e to the power I alpha 1 tau 1 plus alpha 2 tau 2 plus alpha 3 tau 3. Okay. So these alphas are real numbers which specify the point on the manifold that describes SU2. We know that from the definition of SU2, we can find that SU2 is actually, the coordinates of SU2 take value in a three-dimensional sphere. So at a point on a three-dimensional sphere, if you look at the intrinsic coordinates, there are three numbers. And we are choosing those three numbers to be alpha 1, alpha 2, alpha 3. So a better way of drawing this is that we have three numbers here. So this is some point P on S3. P, of course, corresponds to the fact that S3 is also a group. This corresponds to a fact that P is also an element of SU2. And because it's a manifold, that means that we can find a local neighborhood of P such that we can find a projection such that, this local, neighborhood of P gets projected to a subset of R3. And this projection, this map, if you like, let's call it phi. And then the points, the coordinates of the point P in this map is phi is phi of P. And this phi of P is what we are calling alpha 1, alpha 2, alpha 3. Okay? So this is what it means.
means
Yeah.
to compare the input set with a sphere S3 and using a mapping to find the alphas and using that to generate U, alpha 2, U alpha 3.
Right. So, let me give you, this is basically what is how a manifold is covered by coordinates. This is a general picture of a coordinate system covering a manifold. Okay, so you actually know this, but you have not been told that you know this. Let me give you an example with two-dimensional sphere S2. S2 is not a group. Sorry. But S2, of course, is a manifold. So you all have seen globes, right? So this is a globe. And this is the North Pole, say. And there is a South Pole somewhere, which is on the other side, right? And the South Pole is somewhere there. Okay, now the thing is that it is obvious that S2 is not equal to or is not R2, right? But we can cover most of S2 by a subset of R2, and we can do it in many, many different ways. A very common way of doing that is known as the stereographic projection. So what we do is that we imagine that the two sphere is sitting on an infinite two-dimensional plane, and R2. And we can even think of it as a C1, but R2 is better. So, and then what we say is that every point on the sphere, suppose this is some random point on the sphere, P, we are going to project this point onto the R2 by drawing a line from the North Pole to the point, and then, extending that line until that point hits a point on R2. So sorry, this should be a straight line. So this is a particular projection. Let's call it phi 1. So the point here, this is the coordinate of the point P. So we call it phi of P. And it'll have an X coordinate and a Y coordinate, right?
It's like shining a light, right?
Shining a laser light, exactly, but from the North Pole. Right, so now you see that all the points which are in the southern hemisphere, so the point over, the point on the, over here will be just this point, right? It'll be projected down to the point over here, right? And all the points on the equator will be, projected onto a circle, and that circle should actually be smaller than it should be. It's going to be some circle, right? Right but the North Pole itself gets, it's an ambiguity. As you come closer and closer to the North Pole, the points, this point goes off to infinity, right? And this point goes off to infinity. That point goes off to infinity. This point goes off to infinity. So the North Pole itself is not going to be part of R2. So you see that we cannot cover the whole of the manifold by a subset of R2, right?
Yes.
So we need, if you want to cover the whole so this is what it means when we say that, a manifold is a topological space which can be locally, and the word local is the important word, locally represented by some open neighborhood of Rn. In this case, it's R2, okay? Or an n-dimensional manifold. So here, local means that it's not, it cannot be globally covered. So here we see that the North Pole is excluded from this particular map. Okay, so we can fix this. We can think of another map. We can think of another, say, R2, which sits on top. Now the R2 touches the North Pole. So there we will see that. And then what we do is that we make the analogous rule that if there's a point on the sphere, say Q, let's call it Q, then we project it onto this new R2 by drawing a line from the southern hemisphere, and the point that intersects this R2, we call it phi 2 of P, and phi 2 of P is going to be another set of coordinates, x prime, y prime. Now I leave it as an exercise for you to find the relationship between x and y and x prime and y prime. Okay, so this is an interesting exercise in geometry that find x as a function of x prime, y prime, and y as a function of x prime and y prime. Okay. Okay, so now this is in chart number 2, we see that we can cover all points except the South Pole, right? So, but with these two charts, union of these two charts, phi 1 and phi 2, we can cover all of S2.